Welcome to the tutorial on flip-flop conversions. In the conversion of flip-flops, what we are going to do is we will be trying to convert from one type of flip-flop to behave like another type of flip-flop. So in order to do that, we will make one flip-flop mimic the behavior of another type by adding some additional circuitry or making some necessary changes. So there are two steps that are involved in this process. The first step is to write the application table of the flip-flop and the next state table of the desired flip-flop. In the second step, we are going to obtain the excitation table for the two flip-flops from the application table and the next state table. So this excitation table will provide the details regarding the inputs which must be provided to the flip-flop to obtain a definite next state from the known current state. The next state usually is represented as Q plus and the present state is represented as Q. So we are going to adapt the same technique for all the flip-flop conversions. So let us quickly look into the first one. So here we have to convert the SR flip-flop to D flip-flop. So I'm going to write the application table of the SR flip-flop wherein I have the inputs Q and Q plus. This is the present state and this is the next state. So this application table we have already seen how we obtain this when we studied regarding the characteristic equations. And moreover, we are going to obtain the next state table of the D flip-flop. In the excitation table, we will be combining the next state table and the application table. First, what we are going to do is we are going to write the next state table as it is. Looking at Q and Q plus, that is these parameters, we are going to write the values of S and R. So you need to be very careful when you write S and R, because if you observe here, this is 0 0 1 0 0 1 1 1, whereas this is 0 0 0 1 1 0 1 1. So when you write the values of S and R, be careful to ensure that you are observing the pattern clearly. Once S and R is written, that is your complete excitation table is ready, we need to write or simplify using the Karnaugh map. So I need to do that individually because we have two variables S and R here. So I am going to map this particular min term and this particular don't care term. Similarly for R, I am going to map this particular don't care term and this particular min term. So on mapping and grouping and simplification, I obtain S to be equal to D and R to be equal to D bar. So if you look at this particular logic diagram, you can see that we are converting an SR flip-flop to D flip-flop. So SR flip-flop is drawn and from the equation S is equal to D, so D is directly given to S and R is the inverted version of D. So we make use of an inverter and then provide it to R. A clock has been provided. So this clock can either be positive edge triggering or negative edge triggering. It is specifically specified that it has to be a negative edge triggering. Ensure that you provide a bubble at the clock. So this is the procedure that we are going to follow for all the flip-flop conversions. That is, first we will generate the application table for the flip-flop that is already available to us. We will try to obtain the next state table for the flip-flop that we are going to convert it to, and then obtain the excitation table, simplify using the Karnaugh map, and finally draw the logic diagram. So second, we have the conversion of SR flip-flop to JK flip-flop. Now here first what we need to do is we need to write the application table of the SR flip-flop. So this is exactly the same like the previous conversion. So we have the application table. Now when we draw the next state table for the JK flip-flop, as you know that we are having a total of 8 input combinations. So this we will reduce and this is what we get. If you want to know how we have obtained this. The detailed version of converting from next state table to the application table is available in the tutorial for characteristic equation. So kindly go through that so that you will understand better. So the next step would be to obtain the excitation table. So for the excitation table, first what I'm going to do is I'm going to directly consider the next state table of the JK. So this is completely written here. Looking at the variables of Q and Q plus, I am going to write S and R. From this excitation table, I will be obtaining the K map for S and K map for R. I'm going to map the min terms and the don't care terms. In this particular case, you need to be very careful because this is going to be a 3-variable Karnaugh map. So J, K and Q. That is because if you observe the next state table, the next state table had 3 variables J, K and Q. So that is the reason you can see that the Karnaugh map is of 3 variables. So here you need to provide the different possibilities for K. That is, if it is a dash, that means it can either be a 0 or it can be a logic 1. So based on that, it will be having 2 don't care terms and 2 min terms. Similarly, for the Karnaugh map of R, you have 2 don't care terms and 2 min terms. Group the min terms and you obtain the expression as S is equal to JQ bar and R is equal to KQ. So since this conversion involves SR to JK, I'm going to draw the SR flip-flop with a positive clock, and the expression says that S is equal to JQ bar. So I need to make use of an AND gate. So AND gate JQ bar. So this is shown in green color, and you also require another AND gate to indicate K and Q. So this is being indicated with the red color. So this way it is possible for us to convert from SR flip-flop to JK flip-flop. The next one is SR flip-flop to T flip-flop. In this particular conversion, we are going to write the application table of the SR flip-flop, the next state table of the T flip-flop, excitation table which has the next state table of the T flip-flop, and correspondingly we are going to write the S and R values. Now, since we require to simplify for S and R, we require 2 Karnaugh maps. So we need to map these don't care terms and the min terms. So you get S is equal to TQ bar and R is equal to TQ. So based on that, we will require additional AND gates, and we can convert SR to T flip-flop. So if you would have observed, the strategy that has been used for the conversion is same throughout. We obtain the application table, the next state table, excitation table, simplify using the Karnaugh maps, and then draw the logic diagram. So next is JK flip-flop to T flip-flop. So as a first step, application table of the JK has to be obtained, then next state table of the T flip-flop, then excitation table has to be written, and we need to obtain the Karnaugh map for the 2 variables J and K. And in this case, when you group, you have to see to it that you can group even the don't care term, and this way you get J to be equal to T and K to be equal to T. So JK flip-flop is converted to T flip-flop as shown in this particular logic diagram. Next is JK flip-flop to D flip-flop. So to recall, again JK application table has to be written, next state table of the D flip-flop has to be written, excitation table of D flip-flop and respective JK has to be written. J and K are the 2 variables for which K map has to be simplified. J is equal to D and K is equal to D bar. That is what is giving you the logic diagram, wherein you will require an additional inverter circuitry to be added for the conversion. Next we have D flip-flop to T flip-flop. So application table of the D flip-flop is drawn. Next state table of the T flip-flop is drawn, and in this case we are going to have the excitation table, and for the D flip-flop or for the D, you are going to use or simplify the Karnaugh map, and the expression that you get is TQ bar plus T bar Q, which is equal to XOR operation. So the D flip-flop can be converted into a T flip-flop by including an additional XOR gate. The next one, if you observe, is T flip-flop to D flip-flop. The previous type was D flip-flop to T flip-flop, and this is T flip-flop to D flip-flop. So here it is just the opposite. The application table of T flip-flop is written, the next state table of the D flip-flop is obtained, excitation table is written, you are going to have the Karnaugh map for the T, and T will be equal to D XORed with Q. So if you observe or compare the circuit, you would observe that it's just that T is replaced with D for converting T to D and D to T. So this is almost similar to the previous one. Next we have the conversion of D flip-flop to JK flip-flop. So here first we need to write the application table of the D flip-flop, then the next state table of the JK flip-flop. When you obtain the JK flip-flop next state table, you will have 3 types of input variables, so hence 8 input combinations which need to be simplified so that you obtain the table in this particular form, and hence you can obtain the excitation table in this form. Using this excitation table, you are going to use a 3 variable Karnaugh map to deduce, and you will get this as JQ bar. So JQ bar plus J bar Q, K bar Q, and hence you require 2 input AND gate, 3 input AND gate, you require an inverter, and you require an OR gate, and this way you can obtain the logic diagram. So everywhere in all the conversions, if you observe, one important thing that you would notice is that it is by adding an additional circuitry or additional interconnections, it is possible for us to convert from one type of flip-flop to another type of flip-flop, and all that is required is the knowledge of the application table and the next state table, from which we can generate the excitation table, simplify using the Karnaugh map, and obtain the required conversion expressions.